If you remember, in the last lecture we have learned about norm vector spaces, inner product spaces, etc. And we have seen different types of norms there, like Manhattan norms, Euclidean norm, that is L2 norm. Then we have seen P norm and maximum norm, that is L infinity norm. In this lecture we will continue from the inner product spaces and discuss about two of very important concepts related to machine learning, that is orthogonal complements and projection operators. These projection operators are really very important when you do the machine learning algorithm. Those are popular nowadays, especially like dictionary learning algorithm, etc. So, first let us define the orthogonal vectors. So, in an inner product space V together with norm, two vectors V I and V j are said to be orthogonal if their inner product is 0. So, this orthogonalization is a generalization of the concept of perpendicular vectors. As I told you in previous lecture that one of the inner product on Rn is usual dot products of vectors. So, usual dot product, if you take two vectors and then their dot product is 0, we say that the two vectors are perpendicular to each other. So, in the same way, these are the generalization, this orthogonal concept is a generalization of the perpendicular vectors for any vector space, where you can define orthogonality in different way. So, if you want to see a simple example of orthogonal vectors, so just take your vector space as R3, define over the field of real numbers and take two vectors 1 0 0 and 0 1 0. Then if you take the dot product of these two vectors, which we are taking the inner product also in this case with R3, then the dot product is 0, hence two vectors are orthogonal and they are perpendicular also, because first vector is defining the x axis while the second vector is defining the y axis. Now, what is an orthogonal complement? So, take W as a subset of an inner product space V, then the orthogonal complement of W denoted by this symbol W, and in superscript you are having this orthogonal symbol, is the set of vectors in V that are orthogonal to every element of W. That is, W orthogonal is V belongs to all vectors V belongs to the inner product space V, such that the V is orthogonal to W for all W belongs to the set capital W. So, if you want to take an example of this, so let us take W as 1 0 0 and 0 1 0. Now, you take an inner product space is here R3 over the field of real number, and the inner product is usual dot product between of the vector of R3. Now, what is the orthogonal complement of W? Then it is a space subspace of R3 spanned by the vector 0 0 1. So, you take any vector of this subspace, that is orthogonal complement of W, and take the inner product with the vectors of W, it will give you 0. So, as I told you, this orthogonal complement of a set W is always a subspace of V. Here there is no restriction on W. W may be a set of V or it may be a subspace of V. So, as I told you, there is no requirement on W to be a subspace of V. However, orthogonal complement of W is always a subspace of V. If W is also a subspace of V, then the vector space V can be written as the direct sum of W and orthogonal complement of W. What is the meaning of this direct sum? That every vector small v belongs to the vector space capital V can be written uniquely as V equals to VW plus VW complement, where VW is a vector in W and VW complement is a vector in W complement. So, if you see the earlier example here, as I told you, so here W is also a subspace, and then you take any vector, let us say 2, 3, 5, then I can write it 2, 3, 0 plus 0, 0, 5. So, now this 2, 3, 0 is a vector in this subspace. So, W is here, the subspace is spanned by these two vectors, because 2, 3, 0 I can write as 2 times 1, 0, 0 plus 3 times 0, 1, 0. So, it means 2, 3, 0 belongs to the subspace W and this belongs to the subspace W complement, because it can be given by this subspace. It is an element of, it is a vector of this subspace. Now, come to another important definition, that is orthogonal projection. So, now we are going to define orthogonal projection. So, let V be an inner product space and W be a subspace of V. Also, let W1, W2, Wk be a orthogonal basis of W. Here meaning of orthogonal basis is that all these vectors W1, W1, W2, Wk are orthogonal to each other. Now, the linear transformation Pw from the vector space V to W define as Pwv for a vector small v belongs to the capital V as the inner product of Vw1 plus inner product between V Wk upon square of the norm of Wk multiplied with Wk is called the orthogonal projection onto W. So, let us see an example of this orthogonal projection. So, let W1 equals to 3 0 1 and W2 equals to 0 1 0. Define W as linear span of these two vectors W1 and W2. Now, take a vector V equals to 0 3 10 belongs to R3. Now, what will be the orthogonal projection of this vector V onto the subspace W? So, it is P of W of V as I defined in earlier slide, V W1 upon square of norm of W times W1 plus V W2 upon square of the norm of W2, and here you can notice that W1 and W2 are orthogonal, where inner product is usual dot product of vectors in R3. So, now what is dot product between V and W1? So, it is 3 into 0 plus 0 into 3 plus 1 into 10. So, 10 upon the square of the norm of W1, that is 9 plus 1 10 times W1, that is 3 0 1 plus inner product of V and W2. So, that is usual dot product of these two vectors. So, 3 upon norm of W2, that is 1 into W2 0 1 0. So, it comes out to be 3 0 1 plus 0 3 0, which is 3 3 and 1. So, this is the projection of V onto subspace W. If you take a vector V minus the projection, that is V is here 0 3 10 minus 3 3 1. So, this is a vector minus 3 0 9. So, this vectors belongs to the orthogonal complement of W. Now, we are having several properties of orthogonal projection. So, first property is for any V belongs to capital V, the vector V minus BWV is orthogonal to W. So, you can see here as we have calculated it here. So, this is V minus BWV. So, this vector is orthogonal to W1 as well as W2. You can easily verify. So, here 3 into minus 3 minus 9 plus 9 0. Similarly, here 0 plus 0 plus 0. So, this V minus BWV is orthogonal to W1 as well as W2. So, it is orthogonal to W. Second property is the projection of W on the subspace W is W for all W belongs to capital W. The third property is P square W equals to PW. Fourth property is for any V belongs to capital V, the norm of PWV will be always less than equals to norm of V. The fifth property is for any V belongs to capital V and W belongs to capital W, V minus PWV and norm of this vector will be always less than equals to V minus W. That is, if PWV is such W belongs to the subspace W which minimize the distance between V minus W. So, this particular property we can use to find a point in subspace W, a vector in subspace W which is closest to the given vector V. We will see it by an example, but before that let us see the definition of projection transformation. So, any linear transformation P that satisfies P square equals to P is called a projection. So, here this orthogonal projection is also a projection. Another example is, trivial example is identity. So, as I told you, the property 5 of slide 6 shows that orthogonal projection solves the minimization problem of finding the closest point in W for a given V belongs to V. This is quite useful in machine learning where we need to find closest vector in a subspace to a given vector in space. So, let us see an example of it. So, find the closest point to V equals to 2, 4, 0, minus 2 in a vector space W which is a linear span of the vector 1 1 0 0 and 0 0 1 1. So, how to find it? We will use property 5 of earlier slide. So, let W1 equals to 1 1 0 0 and W2 equals to 0 0 1 1. Then the closest point to V is, let us say, W cap, and it will be the orthogonal projection of V on the subspace W. Which comes out to be 3 3 minus 1 minus 1, which is belongs to W. So, this is an application of this orthogonal projection, and this application is really useful in machine learning when you are having the space of different classes and you have to find out for a given vector the nearest vector of another class. So, in this lecture we have talked about orthogonal projection, projection operator, and how to find out the nearest vector into a subspace for to a given vector of the vector space. I hope you have enjoyed this lecture. You can follow these references for having more examples, for having more clear concepts. In the next lecture, we will talk about another very important property of linear algebra. Those are related to the linear transformation or matrices, that is eigenvalues and eigenvectors, and those are having tremendous applications in machine learning. Thank you very much.